Okay, so how is everyone today? Good? All right. So when we left last time, we were talking about sets and intervals and various operations on sets and things like that. So to sort of recap, last time, we said that an interval is a contiguous, non-empty contiguous subset of the reals. So an example would be something like -3 to 8, like that. So you could draw this in this way. Like here's the real line, and then we could say, all right, here's -3, and I drew a dot there and filled it in, and then here's 8, and I'm not going to fill that dot in. So why am I not filling that dot in? What's the significance of that? Right, it's not included, and visually that significance is this round parentheses, and then like that, square parentheses mean -3 is included. You could write something like this, so like 7 to infinity, something like that. So in this case, 7 might be like right there. 7 to infinity, so that means 7 and all the way to the right. So that's this first one is a finite interval, this an infinite interval, and then just as a curiosity, I could say, well, what would the set like this one be? So 2 to 2, like this. So it would just be that one point. And that's it. All right. So that's an interval, according to the definition anyway. Good. I have a question. So is the set -3 to 8, like that one we drew there, the same as -3 to 7, like that? So try and think about that for a moment. Are those the same? No, they're not the same. But wait a second. If this is numbers up to but not including 8, isn't 7 the number that comes before 8?
The integer that comes before 8.
All right, it's the integer that comes before 8, but it's not, Are there any numbers between 7 and 8? Yeah, there's a lot of them in there, actually. So the answer to this question is no. No, because in the end you could plot them both and just have a look. So -3 to 8, plotting this one would look like this. And then -3 to 7, including 7, would look like this one. And then, in some sense the question becomes, did I plot the same thing twice? No. because, for example, this point right there that I'm pointing to might be like 7.6. 7.6 is in that one, but it's not in that one, right? So can you see these are not the same set? I always take the time to point this out because many students can kind of think that these are the same thing. So if you initially thought these are the same thing, in the end, I suspect that at any rate, you're overlooking the fact that there's other numbers besides integers. All right, good. Then, concerning sets, generally, we defined complement of a set and I'll just write down the diagrammatic representation. So if we say that that's the universe set and this set right here is set A, and this is the universe set, and this is just like the skeleton of where A is. So then A complement is denoted as A superscript C, like that. And then what do I need to shade in to indicate A complement? Right. Everything that's not shaded in over there. All right. So to give an interval example, we could say something like, okay, how about -3 to 8 complement? Suppose we want to figure that out. All right. Well, we could draw two axes and say that this one is -3 to 8. And this one should be -3 to 8 complement. So for this one, this would be -3 to 8, like so. So that's -3 to 8. So what would -3 to 8 complement be? Well, yeah. So like for this to draw this one, we had to indicate 8, and it's open. So how about down here? Yeah, we're gonna still gonna indicate 8, but it's gonna have to be closed, filled in. Similarly, we had to indicate -3, and it's filled in. But how about down here? Now it's open. And then instead of shading in the middle here, we're going to shade on the outsides. All right. So as a result, we could write therefore -3 to 8 complement really consists of, if we wanted to write it in interval notation, it consists of two different pieces, that piece and that piece. Okay, so then how do we write just that piece? Very good, so -infinity to -3, and then like that. And then ignoring that, and how do we write just that piece? 8 to, yeah, bracket on the 8, and then to infinity like that. And then how do we say that the complement is means you have to be in that piece or in that piece? The union, right? All right. Any question about that? Okay, so that's complement, and then 3. We also said union of two sets. So union of sets. So, diagrammatically, if that is set A, and this one set B, then union means that you're in one set or the other set or both. And it's denoted with that U looking symbol. It's not a U, but it kind of looks like a U. So the union is all of that stuff. So you're either in the one set or the other set or in both sets. All right. So to give an interval example, we could calculate, say, how about 10 to 17 union 2 to 12, like that. Okay, so the way to go about this is that we're going to draw three axes: one for the first interval, one for the second interval, and a third one for the answer. All right. So one for the first interval, one for the second interval, and one for the answer. So this will be 10 to 17, this one 2 to 12. So we've got four numbers there: 10, 17, 2, 12. We need to plot them in the correct left to right order. The absolute position doesn't matter, but the relative order does matter. 10 and 17 I want to be plotted on the top one, 2 and 12 on the middle one there. So of those four numbers, 10, 17, 2, 12, which is least? 2. So I'll put 2 right there. Okay, excluding 2, now which is least? 10, so I'll plot it. I just need it to be to the right of 2, and I need to have enough room to where I get the other two numbers in there also. So excluding 2 and 10, which number is least? 12. And then excluding 2, 10, and 12, which is least? 17, right? It's the only one. All right. So now we have them. We have the left to right order correct. So 2, 10, 12, 17. So 10 to 17 will have both endpoints. So included, and all the stuff between. So that's 10 to 17. And then 2 to 12, we're gonna include 2, but not 12. Like that. All right, and we want the union of these. So over here, the condition was you're in set A, or you're in set B, or you're in both. It's the same thing here, but because I also use some colors, I can say it with color. So we want all of the points that are colored red, or they are colored green, or they're colored both. So these axes, they all line up. So like this might be like 1.5 or something like that. So 1.5, 1.5, 1.5. So is 1.5 colored red? No. Is it colored green? No. So to be in the union, we need it to have at least one color, red or green. So that means that this point is not part of it. So conceptually, you can kind of imagine that this line is going to start sweeping until we start hitting a color. Okay, so then do 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 do. Oh, we hit a point, right? So now we have a color. So that means that 2 is colored green, so it must be part of the union. Okay, so then 2 is part of it. And then now we're going to start sweeping, and we're going to just, in a sense, just record all of the points where we have at least one color. So, we sweep. Oh, something's different now. Are we still in the union? Yeah, because now we have more than one color, right? But we only need one. Okay, so we keep sweeping, so sweep. Oh, something changed. Now what? We're still in the union? Yeah, because we lost green, but we still have red. Okay, so then we sweep, and then beyond 17, there's no more color. So as a result, what's the union? 2 to 17. So we can say, therefore 10 to 17 union 2 to 12 can be written the simplest way in interval notation as 2 to 17. Any question about that example? All right, so I have a question. So on this thing, we're saying that this union right here, simplifies to that interval right there. So this simplifies to that. Does this union simplify? Why not? Why does this union simplify? That one simplifies to that, but this one doesn't simplify.
Because that has no overlap.
Right. So the question is do these two pieces, do they have any overlap? The answer is no. It's clearly that this is one piece, and that's another piece, and the pieces are not contiguous. Whereas, do the red and the green, do they have any overlap? Sure, right there. Good. Any question about this? Okay. So the last set operation that we need for our purposes is intersection. So diagrammatically, it is like this. So if this is set A and this is set B, then the intersection, so set A, set B. So, union is written A and then the union symbol B. And intersection is written quite similarly, but the union symbol is turned upside down. So it's like this. A intersect B. And the points that are in the intersection are the points that are in both sets. So we need the points that are in set A and also in set B. So can you see where those are in the diagram there? Is this a little bit right there? All right. Fine. So to have an interval example, we can do the intervals on the previous page. We could say, for example, let's calculate calculate 10 to 17 intersect 2 to 12. Okay, so the setup for this calculation is the same as for union. We're going to draw three axes, one for that interval, the other for that interval, and then the third for the result. So 2, 10, 12, 17. All right. So, when we were doing union on the previous page, the condition was we want all the points that are colored at least once. They're either colored red, or they're colored green, or they're colored both. That was union. What is the condition for this one? Yeah, we need all the points that are colored both colors. It must be colored red and also colored green. Okay. So, again, so starting like over here, this might be like 1.8 or something like that. So 1.8 is not colored red or green. So, and what we're looking for is both. So that point's definitely not in there. So how about something like that one? That might be something like 3. Is 3 in the intersection? No, because it's colored green, but to be in the intersection, it needs to be colored both colors. So what is the least point that has both colors? 10, right? Right there. So then that means that 10 is part of the intersection. So why is 10 part of the intersection? Yeah, because it's colored red and it's colored green. All right. So then from here, we can sweep to the right and just keep track of where do we have both colors. So you can see that, okay, something happens at 12. So is 12, so I'll mark 12, like so. And then my question is do I fill in 12 or do I not fill in 12? No, but I filled in 10. Right. So then, having a look at that one. So to be in the intersection, it has to have both colors. So 12 is colored red. That's good. But it's not colored green. That's bad. Right? So this is the answer. So we could say, as a result, therefore the intersection 10 to 17 intersect 2 to 12. What's the simplest way to write this in interval notation? Very good. 10 to 12. Any question about this one? All right. So then maybe one example, and then we'll move on to something else. How about let P be, I don't know, -3 to 8. That was what we used on the previous page, I think. And let Q be, I don't know, 5 to infinity. Yeah. Find P complement intersect Q. So, in one part, and also find P complement union Q. All right. So this is like, like part 1 and then part 2. Okay. So it seems to me that a good strategy for this, since P complement is used, in both places, maybe we'll just go ahead and compute P complement now. So, sort of like step 1 here. Find P complement. So if this one is P, then that would be like this. -3, 8. So there's P. And so P complement must be this. All right. Any question about just that bit there? All right. Then for P complement intersect Q, so again, this is just like we did one right there. So 3 axes. One for the first set, one for the second set, one for the result. So for P complement, we kind of need to mark out 2 points, -3 and 8. And what do we need to mark out for Q? Just 1 point, right? We need 5. Okay. So P complement would be like this. So -3, 8. Like that. And then Q, for Q, we have 5 to infinity. So 5 is in between those 2 numbers, so something like this. And it's included. And then because it says 5 to infinity, it's something like this. All right. So we want the intersection. So P intersect Q. So how do you see it from this situation? Maybe in terms of color. So how do you what I'm asking is, how do you state the condition that we're trying to find?
Numbers that are on both lines, complement P and Q.
Right. So yeah, we want all numbers that are in that set and also in that set. And in terms of coloring or shading, we want numbers that are colored red and also colored green. So we want both. So nothing back here could be part of the intersection, because green doesn't even start until 5. So but even 5's not in the intersection, because what we need is we need both colors. So where does what points have both? 8 to infinity. So all of these. So then, we could write it in interval notation. We could say that P complement intersect Q in interval notation is what? Eight to infinity. Like so. And then, to find the union, P complement union Q. So again, P complement Q, and the result. right. So now we want union. And so now what's the condition that we're looking for? Okay. So I'm not sure what you mean there. Because this one to me kind of seems like overlap. So opposite of this one, that would be the complement of this. Well, let's think about it. Remember what union means. So intersection, in terms of colors, means both colors, this color and that color. So intersection means red and green. Yeah, or both. So union is red or green or both. Okay. Very good. So all of these points have at least one color. So these have only red, but that's enough. These right here in this little bit have only green, but that's enough. And these are red and green, and that's enough. Okay, so then P complement union Q is negative infinity to negative 3 union 5 to infinity. Any question about this? Any question about it? So, it's fun to, come up with sets and calculate complements and unions and intersections and what have you. But typically, we'll have some exercises that are like that. But typically, this comes up as just a part of an exercise. So here's an example. So it's going to be something like this. So here I'm going to make an exercise. So specifically, the kind of exercise that we're going to make is that, we've done the kind of exercise where I give you an expression and I say, find the domain. Okay, and then you say, well, you didn't give me a domain, so the domain must be the natural domain, and then you go calculate something. Okay. Now, what I'm going to do is I'm going to give you an expression that has to satisfy two different requirements. It's got to satisfy this requirement. It's got to satisfy that requirement. And because it has to satisfy both requirements, the first requirement will give you a set, and the second requirement will give you another set. And because all requirements must be satisfied, how do we calculate the answer? If these things and those things must be true. With intersection, right? It's just like, if you want to go to dinner and with a buddy, and you say, well, I'd be willing to go to any of these places. And then your buddy says, and I would be willing to go to any of these places. Well, to make it work out between y'all, you've got to find out, you've got to compute the intersection of the sets. And say, well, okay, I guess it's going to be Taco Bell or whatever, Fine. So the first requirement, I'm going to make an easy quadratic. All right. So then the way I'm going to do that is I'm going to select two integers, one positive, one negative. So just to speed things along, I'll choose them. So how about negative 8 will be one of them, and positive 5 will be the other one. So what I'm going to do is I'm going to say x plus 8 multiplied by x minus 5. Now, I said negative 8, but then I wrote x plus 8. The reason why is because notice that concerning this expression, if you plug in negative 8, then that's 0. That's what I wanted. And if you plug in positive 5, that factor is 0. Right. So I'm going to FOIL this. Multiply out, collect like terms. So this would be x squared and then plus 3x minus 40. Fine. And so now I'm going to choose a point in the interval -8 to 5. So somewhere I'm going to choose some point in here. And then, just to make it slightly adventurous, since we made this one an easy quadratic, I'm going to choose a number that's in here, but it's not going to be an integer. So how about we choose something like, I don't know, 3.2. All right. So. So now, again, I'm making an exercise. So that's what I'm doing. So you're like watching it happen. So I chose these two numbers, and then I kind of hid them just a little bit by making this quadratic. And so now I chose another number, 3.2, and I'm going to hide it just a little bit. Okay, so, and the way I'm going to hide it is like this. I'm going to say that, okay, I did that, and now I'm going to say that, okay, x is 3.2. And, well, if I multiply both sides by 5, so 5x is 5 multiplied by 3.2. Well, what is 5 multiplied by 3.2? 16. So this would be 5x is 16. And so now I'll say 5x minus 16 is 0. All right. So this is enough for me to make the exercise now. So here's the exercise. Find the domain of the square root of 5x minus 16 divided by, no, I didn't want to write that. The point is for me to multiply it out. X squared plus 3x minus 40. So find the domain of that. Okay. So remember the rule. So you're given an expression, and no domain was explicitly given. So there's no explicit domain. And therefore, the domain is the natural domain. All right. And then, can you remind me what natural domain is? What is that? So this is like one of the key ideas in the course. Very good. So it's the largest set. I love it. The largest set of inputs for which the expression is defined. Okay. So it's saying what x's can you plug in? All right. So natural domain is the largest set of inputs for which the expression is defined. Okay. So at this point in the course, there's just two concerning expressions. There's just two ways that we could get to something that's undefined. So what are those two ways? Divide by 0, that's one of them, and negative input to an even radical. So now, effectively what that means is that we want to avoid divide by 0, and 2, negative input to an even radical. Now, we've done several exercises that amount to find the natural domain before. But if you look back, it's always been the case. It's always been the case that it was one of those, but not these, or the other way around. It was either there were divisions by 0 and no radicals, or there were radicals but no divisions by 0. Now, this exercise is the first one where we're going to have to deal with both. So the way that we're going to do it is we're going to figure out the one condition and then set that answer aside. Then we're going to figure out the other condition and set that one aside, and then we're going to say, okay, we need both conditions to be true. So we're going to compute an intersection after that. All right. So I'll do it with numerator and denominator. So concerning the denominator, if the denominator is 0, that's where we have a problem. So we need to solve the equation x squared plus 3x minus 40 is equal to 0. And then, oh look, it's a quadratic. Is that one of those easy quadratics? It is. How does it factor? So, all right. Does it seem kind of forced that we have the answer right there? Yeah, maybe. But I'm showing you the way these are made so that you can understand what it is that I'm looking for. So this is x plus 8 multiplied by x minus 5 equal to 0. And then now, can you see that, yeah, if you plug in negative 8, that factor would be 0. And if you plug in positive 5, that factor would be 0. All right. So these are the places where there's a problem. So this is the places where there's a problem. So where the denominator is concerned, the set that's okay is the complement of that. So therefore, the complement of that is, well, you could draw it as an interval. It's saying that every number is fine except for those two. So it's like someone took the whole number line and then just stole away 2 points and said, no, you can't have these are mine. That. And then how could we write that in interval notation? So it'll be 3 pieces. Yeah, So the leftmost piece would be negative infinity to negative 8. What's the middle piece? Negative 8 to 5. And what's the right piece? 5 to infinity. And how do we say that to be in set D means you're in that piece or that piece or that piece? Union, right? This one, or that one, or that one. So that's the, that's where the denominator wants to go eat. This is what's necessary for the denominator. Where the numerator is concerned, what it needs is the input, its input, to be greater than or equal to 0. All right. So we need to solve the equation, or the inequality, I mean. 5x minus 16 is greater than or equal to 0. So that's what we need to be true. All right, how do we solve this? Well, we could add 16 to both sides. So that 5x is greater than or equal to 16. Now what? Divide both sides by 5. So the new left-hand side is x, and the new right-hand side is what? 3.2. All right. So writing this in interval notation, just that set there, we could say n is what? How do we write that in interval notation?
Bracket 3.2 infinity.
Very good. So 3.2 or bigger, like that. So, the way to interpret this is that, we've got an expression. It's a little bit complicated. So what we want to do is we want to figure out what are all the inputs for which this expression can be evaluated. What's the natural domain? So we said, well, let's consider the denominator in isolation. So, as it turns out, at negative 8 and at 5, the denominator is 0. So those are out. So where the denominator is concerned, anything but negative 8 and 5 are allowed. Fine. So if we consider the numerator in isolation, the numerator requires 3.2 or greater. Okay. So then, in order for the whole expression to work, that means that we need this condition to be true and that condition to be true. We need them both to be true. So for the entire expression, we need D intersect N, which means this thing and that thing. All right. So how do we calculate an intersection for the 5th time today? All right. So then three intervals, or three number lines. One for the first one, another for the second one, and then another one for the answer. And again, we've got to get stuff to line up the way we want. So we've got 3 numbers, negative 8 and 5. And for n, we need 3.2. Well, as it happens, those numbers, relatively speaking, fit here. So negative 8, 3.2, and 5, like that. And then, so we don't have negative 8, we don't have 5, but we have everything in between, everything besides. So that's the denominator's requirements. And then for the numerator's requirements, we have 3.2 and everything beyond. So in order for them both to be satisfied, we need both colors. We need the intersection. So what will the intersection be? So what's the least value in the intersection? 3.2. And then we have both colors for a little bit. So we have both, so yes. And then right there we lose 5. So 5's out. What about beyond 5? We're still good to go after 5, beyond 5. So then, you know, there it is. So we can say, therefore the domain is in interval notation. How do you write it?
Bracket 3.2,
Mm-hmm.
comma 5, parentheses, union, parentheses, 5, comma, infinity, parentheses.
Very good. So last two questions. Can this union be simplified? No. Why can it not be simplified?
There's no
No overlap, right? That's two distinct pieces. Finally, notice that this final answer does not include -8. Why not? Right, but you know, like -8's not included in this set, but I had to write it down and stuff. But over here, I didn't have to write down -8 at all.
Because -8 is within the complement of the numerator.
Okay, I like it. So -8 is like way over here. So to make, I want to make this point clear is that you know, what's being among the many things being checked on this exercise, it's being checked that did you find that -8 was a point that you should be looking at? Did you discover that? Yeah, you discovered it. And then did you come to the conclusion that actually, even though -8, you had to consider it, it's actually not part of the final answer because, you know, it's way out in left field. It's way over there. So did you find that? So the reason why I mention this is because, you know, every time I give a question like this, what happens is that somehow a student tries to somehow put -8 in here because they know that -8's important. But, you know, but, you know, it's like it just gets jammed in there somehow. All right, good. So I hope you have a wonderful Monday.